I have IS of t is 2 cosine 10 cubed t amps. Oh, and always look at the units, because sometimes they're like milliamps or something, and then you'd have to multiply by 10 to the negative 3. Vs of t equals 8 sine 10 cubed t volts. And we have a circuit with a current source and then I've got a resistor and an inductor in series. And then I've got a capacitor that's in parallel with that. Yeah, I've got all kinds of stuff here. And I've got, that's a 2 ohm resistor. Here's my Vs. And then I'm going to have my load over here. And I know that I'll have optimum performance when the impedance of the input circuit is purely real. So I want to add something right here I want to add something to make the input purely real. All right, so in order to do that, we need to find out what our impedance is right now. So this first one we can write as 6 plus j omega. Omega is 10 to the third. How did I know that? That's omega. J omega times 0.004. My capacitor is minus J over omega times 0.0005. And then I'm going to do a source transformation so I can get all three of these in parallel. Let me do a little side on source transformations. So I'll come back to this in a minute, but I want to talk about source transformations. So source transformations are useful whenever we have a situation like we were just in, where we've got these two things are in parallel, and then I've got this extra resistor right here that's stuck on this branch with the voltage source, and it really is not conducive to finding the total impedance. But if I could change this resistor to being in parallel with the rest of them, I could do this. And so here's how you do a source transformation. If I have a voltage source and a resistor or impedance in series, that is equivalent to a current source and a resistor in parallel. Now, this resistor has the same value. And if I'm going from a voltage source to a current source, if this is my voltage, then my current source is going to be V over R. Now, if I'm going from a current source in parallel with a resistor, that's a great resistor, to a voltage source in series with the resistor, my voltage source will be IR. So just use Ohm's law to figure out the value. Notice that wherever the positive terminal of my voltage source is, that's the direction that the current source goes. So just real quick before I go back to the original problem, so if I had and I wanted to find the total, and I wanted to find the current right here, then the easiest way to do this is with a source transformation. And this would be 4 amps. And then I could find the value of those 3 resistors in parallel. I would do 1 over 6 plus 1 over 2 plus 1 over 3 would be the value of those 3 resistors in parallel. And then I could find why wouldn't the current still just be 4? Maybe I'd be looking for something else. Let's say I'd be looking for something else. But anyways, that's what I would do. So going back to this one, we'll do a source transformation. And so because we have a voltage source and a resistor in parallel, so the resistor is going to stay the same. It'll be 2. And then this will become a current source, which would be Vs over 2. Now Vs as a phasor was 8 angle 0. So this is going to be 4 angle 0. All right. So now we're looking for, we don't really care about our 2 current sources, but our 2 current sources are in parallel. So if we did care about them, we could add them. But this particular problem is asking us about the input impedance. And so we need to figure out what the input impedance is. So we've got our 3 impedances in parallel. So we have 6 plus, and then 1,000 times 4 thousandths is 4, so 6 plus J4, in parallel with this is 1 over 10,000 times 5 10,000ths is 2. So this is minus J2 in parallel with 2. And all of that is our input impedance. So this would be 6 plus J4 in parallel with minus J4 over 2 minus J2. So that's product over sum. And then minus J4 over 2 minus J2 is 1 minus J. So 6 plus J4 in parallel with 1 minus J. So that's 6 plus J4 times 1 minus J over 6 plus J4 plus 1 minus J. And that's 6 minus 6J plus 4J is minus 2J. Minus 4J squared is plus 4 over 7 plus 3J, or 10 minus 2J over 7 plus 3J is 1.1 minus 0.76J. Okay. So what do we want our mystery thing to be?
An inductor,
We want it to be an inductor. How did you know that?
because the inductor has positive impedance versus capacitors which have negative impedance.
Okay, and how did you know that we wanted positive impedance?
Because we want a fully real circuit, or impedance, and capacitors and inductors are imaginary.
So this is our impedance right now. We want it to be real. We need to get rid of the imaginary part. So we want to add J.76. And we know that in order to get a positive imaginary part, we need an inductor. And we know that the impedance for an inductor is J omega L. So we need J omega L to equal J.76. So J's will cancel. Omega is 10 to the third L equals 0.76, or L needs to be 0.00076 or 0.76 millihenries. And that will get us peak performance.
Was there ever a time he tested a question like this?
Kind of.
Okay, so it's just not solving circuits. Well, I mean, like, in a sense where just not current or voltage, it could be a missing impedance or stuff like that.
Oh, I see a circuit.
Well, I meant in a sense where, like, not finding current or voltages in a specific point or stuff.
No, but you do need to understand. So there are several points here. So one thing, yeah. So something like this would be. I could certainly see something like this on a test to find out, because there was really the parts that were difficult here, let's see. We needed to do the source transformation, so you needed to know how to do that. You needed to be able to combine three things in parallel, which this one you would not have to show your work, so this would not be one where you'd have to worry about not using a calculator. So using a calculator, it's not bad getting that input impedance, and then you just have to set it equal to j omega L.
Okay.
Okay, so another thing that you might have to do is say, so let's try this. What would the current be with this added impedance and a 100 ohm load? What would the current be through a 100 ohm load with this added impedance? Now, what would you need to do that? So I'm saying I add that impedance, and then I'm going to put a 100 ohm load right there. And I want to figure out what the current is through that load.
Can't you do current division?
I'm sorry, which current are we looking for again?
The current through that. So I do current division, and what would the other impedance be?
Would it be the final answer you got? I mean, the final impedance.
Which final impedance?
1.1. Well, I guess, is it this with the missing components?
So what would the current be through a 100 ohm load with this added impedance?
Oh, that would be, then it would be 1.1.
It would just be 1.1. So I could add together my two current sources that I just got from before, and I would have 1.1 and 100, and then I could do current division.